Your lecturer is Dr. John Kaiser. Dr. Kaiser is a professor and the Associate Department Head for Academics in the Department of Computer Science and Engineering at Texas A&M University. He earned his PhD in Computer Science from the University of North Carolina. Dr. Kaiser has taught a range of courses, from introductory computing and programming to advanced modeling and simulation. He has won several teaching awards at Texas A&M, including the Distinguished Achievement Award in Teaching, which he received once at the university level and twice from the College of Engineering.
When I say computer, you probably think of something extremely powerful. Computers can calculate numbers at sizes and speeds that humans can't begin to match. They can record our writing and send it almost instantaneously to anyone around the world. They can help us find almost any information we want, from how to repair a faucet to who won the Cowboys game last night. We've seen computers beat Garry Kasparov at chess and Ken Jennings at Jeopardy! So when we think of everything that computers can do, it's easy to think of them as incredibly smart and powerful machines that humans just can't hope to comprehend. But computers, on their own, aren't really that smart. In fact, you might even call them really, really dumb. Okay, dumb might be too strong of a word, so let me explain a little bit more. At its heart, a computer is just a machine that can do a few basic things extremely well. It can do those things very, very reliably and very, very fast. But on its own, a computer can't do much of anything useful at all. In order for a computer to do any of those things that we think of as so powerful and so intelligent, it needs a computer program. As computer programmers, we are the ones who give the computer the power and the brains to do all the amazing things that we think of computers doing. In essence, the programmers bring the computer to life. Now, a computer really only understands a few commands. And those commands need to be given in the language that the computer understands. That's binary, which is simply a series of ones and zeros. There are a few people who actually learn to decipher the ones and zeros that a given computer sees at the lowest level. These machine instructions tell the computer to do one of those very few commands that it knows how to do. These are very simple commands, things like performing basic arithmetic, or comparing two numbers, or loading a value from memory, or storing it to memory. The set of commands can be different depending on the family of processor running the code. Each command will translate to a binary sequence. Data can also be converted into binary, and the combination of these two forms the machine code. Obviously, though, this is not the way that people naturally think or communicate. So to overcome these difficulties, people have developed higher-level programming languages. These programming languages let us express commands to the computer in a way that people can more easily comprehend. And from very early on, these higher-level programming languages, such as Fortran in 1957 and COBOL in 1959, were developed to let people write code that was independent of any specific computer. Over time, as people had new ideas for ways to organize their thinking and how they'd like to express that in code, more languages were developed. So along the way, we've had BASIC, Pascal, C, C++, Python, Java, and so on. Each of these languages was developed for people to be able to understand and write instructions to the computer. Let me say that again, because it's important to understand. Programming languages are developed for people, not for computers. When people write programs, it's just as important that people understand the code as it is that the computer understands it. For programmers, the code we write is a way of taking our ideas and expressing them in a logical, ordered way. The programming languages we use help us do that. They help us structure our ideas and instructions for the computer in ways that we can understand. Then there's a separate program called a compiler, or an interpreter, that will convert the program into a series of ones and zeros that the computer will understand. Regardless of which language you write a program in, it still has to be translated into computer instructions, those ones and zeros. In fact, we can usually accomplish the exact same thing in many different programming languages. So it seems kind of redundant then to have all these different languages, doesn't it? I mean, shouldn't one language be enough? Well, different programming languages will have different strengths. Some languages are easier to learn. In fact, there have been languages developed just to teach programming concepts. This was one of the main motivations for the development of Pascal, for instance. Some languages are made so that you can have a really close relationship between the programming language and what actually happens on the computer. Fortran and C are examples here. Some languages are developed for a person to be able to read them really easily. COBOL was one of the earliest programming languages, and it was developed with this in mind. Some languages are designed to support a particular style of programming. Java is a language that's designed specifically for object-oriented programming. And then there are languages that let you program easily in multiple styles, and C++ is a great example here. There are a lot of programming languages that are specialized for one particular task. SQL is a language developed for databases. The language R is used for statistics. The main point to realize is that different languages have different strengths, and there's no single right or best language. There will be strengths and weaknesses to every language. For this course, I wanted to choose a general purpose language that's easy for you to put on your own computer, that's relatively easy to learn, and that's useful enough that people use it regularly on real-world projects, not just in toy examples. The language that we're going to use is Python, which has all of these characteristics and more. It's easy to get on your computer. Compared to many languages, it's easy to learn, and it's harder to make big mistakes. And it's powerful enough that people use it regularly in real-world projects. There are many professional software projects developed in Python. Python also doesn't require you to use any one particular programming style. It's a good language for several different styles. Oh, and it's fun. In fact, if you're wondering why this language is called Python, it's named after the British comedy troupe Monty Python. So, let's take a look at a very first example. The code you see is an example of a Python program. That's right, the whole program is one line. Now remember, this is an instruction that we're giving the computer. What do you think this does? It's not a trick question, though I will tell you that the word print has nothing to do with putting ink on paper. What's going to happen when we run this code? Well, this line of code prints the words "Hello World" to the screen. For many people, a Hello World program is the first one they write. In fact, it's a long-standing tradition among programmers, probably dating to Bell Labs in the 1970s, that your first program in any language is Hello World. Let's talk about what's going on here for the computer to be able to run this program. First, we have our computer program that we've written. In this case, the program is one line of code. We could enter this program in a couple of basic ways. We could type it into an interactive window, known as a shell window. The shell window will give us results as we type our code. Or we could enter it within what's called a development environment. In a development environment, we type several lines of code. In other words, we develop the program before we actually let the program work. With either of these methods, we can save the program as a .py file, indicating that it's a Python program. We could even just create a .py file on our own in a text editor. Now, regardless of how we type in and run the program, a computer will need that code converted into machine instructions, a whole bunch of ones and zeros that the computer can understand. Then it's going to run or execute those machine instructions. When the computer follows those machine instructions, it does exactly what they tell it to. In this case, it prints out the letters "Hello World" to the screen. Now remember, computer programs, the things written in a language that people understand, need to be translated into machine instructions that the computer understands. This translation process can happen in a couple of different ways. One way will encounter each line of the program and immediately convert it to machine instructions that are run. This is called interpreting. Another method will take the whole program at once and try to figure out the best machine instructions to do what the program meant to do. This is called compiling. Now, the analogy here is a lot like someone translating a human language. When you have an interpreter, they're basically taking what someone says and immediately translating it into another language. In programming, an interpreter is going to basically take one command at a time, translate it to machine instructions, and let it run. On the other hand, a compiler is going to take all of the code together, look at all of it, and then figure out what the commands for the computer should be. It's more like hiring someone to read or listen to an entire speech, and then producing a new speech in a different language that still gives the same meaning. Sometimes there will be a sentence-by-sentence correlation, but not always. Since this approach is compiling together all the code at once in order to do the translation, we call it a compiler. Now, either way, whether a program is interpreted line by line or compiled all at once, the most important thing to know is that we're taking the program and converting it to machine commands. The basic process of compiling or interpreting involves taking the individual lines of code and converting them to at least one, and often many more machine instructions. Some lines of code are very close to the machine instructions. For instance, the most basic arithmetic, like adding two numbers together, corresponds to just one machine command. It's a very direct, straightforward translation of a higher-level code to machine code. However, there will be additional machine commands to load in data from memory or to load a specific value into the processor. So, even just a simple line of code where two numbers get added together can take 3 or more machine instructions. And at the other end, some lines of code can end up being translated into huge amounts of machine code. For example, calling a function may require only a single line in our program, but it could involve many, many lines of machine code. Finding ways to perform this translation from a high-level language that lets people express ideas clearly to machine language that implements the code efficiently is an active area of computer science research. People are always looking for ways to find the optimal translation of high-level ideas to machine instructions. Now, the programs that convert Python to machine commands are actually a little difficult to classify. They're basically compilers that act like interpreters. But in actual use, we can usually treat Python as though it's an interpreted language. That means we can go through it line by line and understand what it's supposed to be doing. If you hear Python programs referred to as scripts, or Python itself referred to as a scripting language, this is partly just a way of saying that Python is an interpreted language that offers some powerful high-level commands. It can be used to automate complex tasks in just a few lines of code. We can see how Python acts like an interpreted language if we run it in an interactive window. Now, Python installations come with a program called idle that lets you type in Python commands and see them run right away. So, if we type in the Hello World program that we saw earlier and press Enter in the idle window, sure enough, it prints Hello World for us. We can also give basic arithmetic commands and see the results right away. If we type in 2 plus 2, we get 4 back. 8 times 15, that's 120. Raise 2 to the 5th power, that's what that double asterisk does. It raises to a power, there's our answer, 32. 2 to the 100th power, no problem. Let's try another program that's a little more complicated. Say we're creating a game, and we want to welcome newcomers to the game. We want to greet the user and give an invitation to play. So, here's a new program that does this. Now we have 2 lines of instruction for the computer, plus a couple of one-word comments, which are meant for humans. The comments are the lines that begin with the pound sign, which people also call a hashtag or number sign, or hatch mark. When an interpreter sees the pound sign, it ignores everything else on that line. Comments are text that's meant for people reading the code. They're totally ignored by the computer, so their only purpose is to tell someone reading the code how to understand it. Comments can be critical for helping someone understand the purpose of code and the way it's working. And in this case, our comments give the purpose for each of the commands that follow. A greeting, followed by an invitation. Okay, let's look at our 2 lines of code. The first prints our greeting. Now, I'm from Texas A&M, and our usual greeting there is howdy, so that's what I'm printing. The interpreter will convert that line of machine instructions that print howdy to the screen. The next line of code prints out a question. Shall we play a game? Bonus points if you can recognize what 1983 movie that's from. Again, the interpreter will convert that to instructions that get the computer to print out that text to the screen. First, notice that we followed the statements in order. The order that instructions are given is the order that they'll be executed. Computer programs are made of long sequences of instructions. Also, notice that we skipped right over the comments and the blank lines. Just like comments, blank lines are things that we put in there for people to understand the code better. Blank lines help separate different parts of the code visually, so it's clear which things belong together. Throughout your code, it's a good idea to use comments and blank spaces to help communicate what you're trying to do. You should never hesitate to put in comments throughout your code. Comments will help you understand your own code better, both as you're writing it and in the future when you come back to it. And comments are often critical to helping other people understand your code. Since comments are for people, they can be freeform, but for everything else, there's syntax. Syntax is the particular way that you need to write and structure your code in a language, Python in our case, so that the computer understands. Syntax is especially important because, like I said before, computers aren't very smart. They're only going to understand exactly what they're told, and so we need to be very precise in how we talk to them. Sometimes that one little change in spelling or punctuation will make all the difference. For example, commands such as print have to be lowercased. If you try to use uppercase, you'll get a name error telling you that you tried to use a name that's not defined. Also, if you read books or programs with Python version 2, the previous version, you'll notice that the print command didn't have to include parentheses. By the time of Python version 3, the parentheses are necessary for the syntax. Why? Well, print used to be just a statement, but now print has become a function, and you need parentheses to use the function. I realize that you probably won't follow that right now, but I want you to understand that there are lots of nice reasons for the way code appears. And best of all, you really can understand why the syntax works the way that it does. By the time you finish this course, the basic structure of how commands are written will seem much more obvious to you. One of the nice features of Python is that it supports more than one programming style. For instance, procedural programming is a long-standing programming style that involves organizing your computation around a set of procedures, or actions, to be taken to solve a problem. Python supports this very well, with a rich set of functions that it provides and allows programmers to create. We'll start out in this course introducing a procedural style of development. Python also supports, but doesn't require, object-oriented programming. Object-oriented programming organizes the computation around a set of objects and the things that can be done to those objects. Python allows the creation of objects and supports some basic object-oriented principles like inheritance. We'll discuss object-oriented design in the last third of the course. Python even supports a style that we won't need in this course, called functional programming. The syntax of Python is designed to support each of these styles, which can also be combined within a single program. Python also is constructed so that the language syntax itself is relatively easy for people to follow. One unusual but very nice feature of how Python syntax is made easier for people to understand is the use of indentation. Unlike in most languages, indenting is actually part of the code read by the computer. So, whenever you see a top line followed by indented lines underneath, this is not only a helpful way for humans to see the structure of the program at a glance, these same indents are also part of how a computer understands the structure of the program. Let me use one really common analogy for programming. A computer program is a lot like a recipe. To fix the food, you need some ingredients, and then you follow some instructions. Likewise, running a program takes some ingredients, that's the data, and then follows instructions. When we're programming, we're going to be focusing a lot on how to write the recipe. But what we really care about, the thing that's most important, is the dish that we're cooking. Sometimes we get bogged down in the details of recipe writing, exactly how to tell someone to cook something, and we lose sight of the food that we're trying to create. It can be even easier to get bogged down in the details of programming and lose the big picture of the goal that you're working toward. So, as we learn about programming here, I'm going to make sure that you understand the basics, the syntax and techniques of programming that will help you actually create bigger software. Just keep in mind that our coding is the tool that we're using to realize these bigger ideas. So, don't get bogged down in thinking that you need to memorize every last detail about syntax. You'll learn and become familiar with all of the most common commands in this course. However, there's no way that you'll remember all of the syntax for all of the various commands that you'll use when programming. or even the commands that you'll see just in this course. You won't learn every command by heart, and that's totally okay. It's fine if you forget exactly how to do something. The important thing is to know what's possible, preferably along with the general sense of how to do it. And then you can always look up the details of a specific command as needed. That's why there are online references that everyone uses. By the time you finish this course, there are 3 main goals that I have in mind that I'd like you to come out with. First, I want you to understand the basic tools of programming, the fundamental commands and structures that you can use to make the computer do what you want it to. We'll spend most of the early part of the course on these items, learning things like variables and conditionals and loops and functions. Now, second, I want you to understand how those basic tools can be used to assemble larger pieces of software. This is where we face issues of design, how we can assemble code to solve a particular problem. We'll talk about different approaches to software development, like top-down, bottom-up, and object-oriented design. And we'll learn how to use debugging techniques and modules and packages to improve the code that we can develop. Now, these topics will be kind of spread throughout the course, but will be concentrated mainly in the middle lectures. And finally, I want you to understand how data structures and algorithms can help us write programs that deal with deeper and more challenging problems in computer science. Most of these lectures will come toward the end of the course, once we already have some of the basic tools ready to use, and we know how to use them to approach problems. Throughout all of this, though, I want you to get practice in programming. We'll have lots of examples and exercises, but the main thing is that I want you to actually learn to write your own programs, and feel confident afterward about continuing to program and going on to learn even more. Now, this brings me to a point about how you can follow this course. Computer programming is as much of an art as anything else. In fact, one of the most famous and important publications in computer science is a multi-volume work entitled The Art of Computer Programming. Take any art, like painting. Now, you can learn a lot just by having someone explain different painting techniques and demonstrate them and show examples of how they're used. And this can be very mentally stimulating, and it can give you a much greater appreciation of paintings that you see. But you'll understand painting a whole lot more by actually trying to paint. As we go through this course, I hope you'll find the descriptions and demonstrations and examples interesting. And I hope watching will give you a greater understanding of the programming process and appreciation for how computer programs are created. But you'll get even more out of the course if you actually try programming yourself. Get into the habit of thinking that any time during the course, it's okay to stop and run a program. Typing it in for yourself gets you following the code much more closely, and you can run that code that I'm showing for yourself. And then it's also great to change the program that I'm showing and see what happens. It's really okay to experiment. That's one of the great advantages to taking a course this way. You're free to stop and try things out whenever you want. Now, throughout the course, you'll sometimes see a little icon pop up. Those are times that I would particularly suggest that you pause, take some time to think about the question or problem, and then try some programming yourself to find the answer. Programming that may look too obvious or too hard will be a lot more engaging and meaningful if you've already invested some effort toward trying a solution yourself. Let me give you a little preview of what we'll be talking about in the next lecture. We've already seen that Hello World program. Here's a small extension to that. We're going to add a second line to the program, a line that gets input. The input command will ask for the user's name. The name the user types in will be assigned to the variable called name. Then, instead of printing Hello World, we're going to print Hello Name. So, can you guess what will happen when we run this program? Have a guess? Let's see what happens when I run it. The program asks my name. I type in John, and the computer tells me, "Hello, John." So, the program as a whole will ask a user's name and then print a statement saying, "Hello, name that got typed in." This short program helps illustrate several ideas: input, output, and variables. We'll be learning details about all of this and a whole lot more in our very next lecture. Now, stick around right after this lecture and I'll show you how to set up Python on your own computer so that you can follow along with the lectures by trying code yourself. Programming is a great combination of problem solving and creativity. I got hooked writing my first simple computer program on a giant Commodore PET computer back in 3rd grade, and I've loved computer programming ever since. It's also a gateway to what's sometimes called computational thinking. Computational thinking refers to the way we think when using computers to solve problems. It describes how we analyze situations and develop ideas. And it refers to a mindset that many computer scientists see as valuable, not just for programming, but for facing other tasks in life. So, as you learn about programming, it may be that the most important thing you're learning isn't the specific commands to the computer, but rather a set of powerful ways to solve problems and exercise your creativity. I'm honored that you've chosen me to help you learn more about this field that's so interesting, challenging, and just plain fun. I'm looking forward to the next lecture as we learn some of the most fundamental pieces of computer programming: variables, input, and output. To write our programs in this course, we're going to want to get you set up to write programs yourself. There are 2 main pieces of software that I'm going to show you how to set up: Python itself and an environment for using Python called PyCharm. The first thing you need to do is install Python on your computer. What that means is that you're going to download a whole set of files that will let you write and run Python programs on your computer. Once you've installed these files, you'll be able to execute .py files, run an interactive window, and execute basically any Python command. The second thing you're going to want is an integrated development environment, or IDE. Python comes with an interactive program named Interactive Development and Learning Environment, or IDLE, that will let you do some simple programming. But it's not an IDE. It won't provide nearly the range of features provided in an IDE. I recommend getting a full IDE such as PyCharm. This makes it much easier to write, run, and try out your code. You'll have an application that comes up, and you can write your code in that application, manage files, run code, see output, debug, and more, all in that same application. Now, a word of caution worth keeping in mind whenever you're following instructions about going to websites to download and install software. Things can change. Some of the details may no longer be exactly the same. Where to go or what to do may change over time. So if you find things aren't exactly like these instructions, just treat this as another opportunity for problem solving. So to get Python installed, open up a web browser and go to www.python.org. This is the official site for Python, and I'll just note that the entire website is helpful. You can find documentation, tutorials, and examples of using Python on this website. For now, though, we want to install Python on our computer, so you'll want to follow the link to the Downloads page. Now, you'll probably see 2 different options, one for Python 2-point-something and one for Python 3-point-something. Version 3 doesn't work quite the same way as version 2. Many people who are already invested in version 2 because they had large amounts of software written in Python 2 or were just already familiar or comfortable with Python 2, they chose to keep maintaining and developing software in version 2. And so as a result, the 2 types of Python have both continued to be used: version 2 and version 3. The similarities between these are much greater than the differences, but there are some differences. Python 3 is the more up-to-date version. And so, for those of us who aren't tied to any old code from Python 2, we're better off with Python 3. So, follow the link to the Python 3 page. If you're on a Mac, you'll probably want the Mac OS X version. If you're on Windows, get the newest Windows version that your operating system can handle. For example, if you are running Windows XP or older, you might need to download an older version of Python 3. There's also a Linux version. Whichever system you're on, go ahead and download the newest stable release that your operating system can handle. Now, for the most part, this should involve nothing more than clicking a single link. The installation process should be straightforward. The downloaded files will probably ask for permission to be installed, and I'd strongly recommend letting them install in their suggested location. Chances are that this will all go smoothly, and when it does, you should have Python fully installed on your system. Now, the first thing we can do is bring up the interactive shell called IDLE. This name may be a nod toward comedian Eric Idle of Monty Python. Anyway, after your download, you should be able to find a program named Idle somewhere on your machine. If it's not on the desktop or in a start menu, you might need to do a search. Once you've found Idle, go ahead and run it. You should see a window pop up with a name like Python 3-point-something shell. There will be a prompt showing, consisting of several greater than signs. Basically, any command you type into this window will be interpreted as a Python command and executed. Now, our first lecture showed a Hello World program and some examples of calculator-like applications. Try some of those out in Idle. As I said before, Idle is useful, especially for trying out something small. So even though we're going to work in PyCharm later, don't forget that Idle is there for your use. Now, for most of our development in this course, I'm going to recommend that you get a full IDE. There are many Python IDEs to choose from, but the one I'm going to demonstrate is called PyCharm. That's Pycharm. PyCharm is a great IDE. It's simple enough that most people can easily use it for basic Python programming. And it's powerful enough that high-end programmers will still use it. To download PyCharm, you'll need to go to its website. From there, click on the download link. That should bring you to a page where you can choose which operating system you have, Windows or Mac OS X or Linux, and then click on the free community version of PyCharm to download it. When you click that link, it should download a program that you can run to install PyCharm on your computer. Again, go ahead and let it install, and I'd suggest letting it go to whichever directory it would like. With PyCharm installed, you should be able to run it. Somewhere on your machine should be a PyCharm application, and you want to go ahead and run that. When you do so, there should be a window that opens. We want to try to get a program running here in that PyCharm window. There will be two steps. First, click on the link New Project. When you do that, it should prompt you for the name and location for the new project, along with the interpreter to use. The interpreter should default to the Python version that you just installed. For the project title, it'll probably default to one called Untitled. Change Untitled to a new name for the project. Finally, click the Create button. Now, a project is going to be a location where there will be one or more Python files that we are developing. You can think of it more like a directory that will hold Python files. Once we have that directory, we'll need to actually create a file that will be our program. So, we go back to the File tab in the PyCharm window, click on New, and select Python File. It will ask you for a name for the file, and this is where you pick the name for your Python file. Now, there in the main PyCharm window, you should see a mostly blank screen. That window, though, is where you're going to type in your program. Again, let's start with a Hello World program. In that window, type in print, open parenthesis, quotation mark, hello, comma, world, close quotation mark, close parenthesis. As you're typing, you might notice that PyCharm will start filling things in for you. When you open the parentheses, it'll automatically generate a close parenthesis. Same with the quotation mark. Notice that unlike the idle window, when you hit enter after this line of code, you don't see the results of this code. To see the results, you have to explicitly tell the computer to run the program. In the PyCharm window, go up to the menu item where it says Run, and then select Run from that menu. You'll have to pick the name of the program you just wrote. When you do, a new window will appear at the bottom of the PyCharm environment. This is the window showing the output. You should see the words Hello World output there, along with something saying process finished with exit code 0. That last line just means that the program completed without an error. Now, you might have noticed that there was a green arrow in front of Run. After running for the first time, you can click the green arrow at the upper right corner of the PyCharm window, or the green arrow down near the output window to run your code again. The new output will replace the old output, so you won't notice anything new if you rerun the same code. But you can make a modification to your code, maybe add another print statement, or change what the print statement says. Then hit the green arrow to see the results down in the output window. And that's it. You've now created your own Python program and run it in the PyCharm IDE. Let's try writing a new program in the PyCharm IDE. We want to print the results of some of our calculator-like math, like we did in the idle window. Inside the parentheses of the print statement, we can put something other than words within quotations. In fact, we can print math. So try writing a line of code to print the number 10. We just have the word print, open parentheses, 10, close parentheses. Is that what you got? If not, try it out. Type that line into the program window in PyCharm and run the program. It should output 10. Okay, now try something a little bit trickier. Instead of just the number 10, try printing out the results of a calculation, like 37 divided by 3. What do you write? Well, we have just put 37/3 inside the parentheses. Notice that the output comes to 12.3333, although it ends in a 4, not a 3 like we might expect. That's called a round-off error. Computers don't represent fractions exactly, so there's some approximation whenever you represent a decimal number. For most cases, this tiny little error is so small that it won't affect us. Let's try one more thing. It's an experiment that I want you to run to see if you can figure out what these two math symbols do. I want you to take two integers and use the double slash operation between them. For instance, try writing 10//3. The output here is 3. Also, try using a percentage sign as the operator. Write something like 10%3. The output here is 1. And keep trying this with several different numbers and see if you can figure out what the double slash and the percentage sign are doing. Okay, that might have been kind of tricky. The double slash is doing integer division. It divides the first number by the second number, and the result is the integer quotient. Since 3 goes into 10 3 times, the answer is 3. The percentage sign gives the remainder. So the remainder, when 10 is divided by 3, is 1. The percentage sign is also called the modulus operator. Mathematicians would say 10 modulo 3. And there you have it. Basic calculator-like operations written in the PyCharm IDE. Writing a program like this program is a good way to understand a little bit more about how the computer interprets and computes math.